Inside a mechanical watch, tiny bearings smaller than a grain of sand keep every pivot turning, and they are not metal. They are ruby. Not mined from the earth, but grown inside a furnace approaching 3,000 degrees Celsius, one microscopic droplet at a time. White powder becomes a single perfect crystal, then one of the hardest bearing surfaces in precision engineering. The question is why a watch needs gemstones at all. A mechanical watch movement operates under constant, relentless physical strain. Inside, a coiled mainspring steadily releases energy through a train of gears that must rotate millions of times each year. The pivots of these gears, often finer than a human hair, exert immense pressure on the metal plates holding them in place. If steel pivots rotated directly within brass plates, friction would quickly grind the metal into dust, widening the pivot holes and causing the entire gear train to misalign and seize. To prevent this destructive wear, watchmakers position highly polished jewel bearings at every critical contact point. These red components are strictly functional necessities, completely distinct from decoration. Synthetic ruby provides an incredibly smooth, wear-resistant surface when paired with microscopic drops of watch oil. The jewels hold the gear shafts securely in place, keeping the tiny wheels aligned and ensuring that kinetic energy flows smoothly through the movement without losing power. This microscopic interface determines whether a watch maintains perfect time for decades or fails within months. The rubies performing this demanding work are not mined from the earth. Natural gemstones are structurally inconsistent, containing microscopic fractures and chemical impurities that would quickly destroy a watch movement's precision. Instead, these components are grown in controlled factory environments. The technology that made this possible dates back to 1902, when French chemist Auguste Verneuil perfected the flame fusion process. This was the world's first commercially successful method for synthesizing gemstones. Verneuil's breakthrough allowed manufacturers to produce identical, flawless crystals on an industrial scale. By 1907, production facilities were generating 1,000 kilograms of synthetic corundum annually, and Swiss watchmakers quickly phased out natural stones in favor of these lab-grown alternatives. This shift completely redefined the ruby, reframing it from a decorative luxury into a standardized, high-performance engineering component. Synthetic ruby possesses the exact same chemical structure as natural corundum, along with a Mohs hardness of 9, making it second only to diamond. Because it is grown without the structural flaws of natural stones, it can be machined to microscopic tolerances with absolute predictability. Crafting this synthetic material requires transforming raw chemical powders using extreme thermal energy. The journey from loose powder to a solid single crystal ruby begins inside a specialized furnace, where a highly controlled oxyhydrogen flame operates at temperatures exceeding 2,000 degrees Celsius. The transformation relies on an exceptionally pure chemical recipe. The primary raw material is aluminum oxide powder, refined to a purity of 99.999% to eliminate structural weaknesses. To ensure consistent melting, the powder must be sifted to a uniform particle size of 1 to 5 micrometers. To turn this white alumina into a vibrant red ruby, engineers blend in a minute quantity of chromium oxide, typically between 0.1 and 0.3%. This precise dopant concentration replaces a fraction of the aluminum ions in the crystal lattice, giving the final jewel its signature crimson hue. This homogeneous powder mixture is loaded into a cylindrical container suspended directly above the furnace muffle. An automated mechanism taps the container at steady, programmed intervals, shaking the powder through a fine mesh screen. Carried downward by a stream of pure oxygen gas, the dry particles pass into the central tube of an oxyhydrogen burner. At the burner nozzle, the oxygen mixes with hydrogen to fuel a vertical flame that operates between 2,000 and 3,000 degrees Celsius. Precise gas flow regulators monitor the oxygen to hydrogen ratio in real time, keeping the thermal envelope stable. Because pure aluminum oxide melts at approximately 2050 degrees Celsius, this intense heat liquefies the falling powder instantly. The individual grains of alumina and chromium oxide fuse in mid-air, transforming into microscopic droplets of molten corundum that descend through the center of the furnace. At the base of the furnace chamber, these falling droplets land on a ceramic support pedestal known as the candle. This support rotates steadily at up to 30 revolutions per minute, distributing the extreme thermal energy evenly across the landing zone. As the very first droplets strike the pedestal, they cool slightly and solidify, establishing a tiny, stable seed crystal. Once this foundation is laid, the automated mechanism begins to lower the pedestal at a highly controlled rate, typically between 6 and 25 millimeters per hour. This slow downward pull is timed to match the exact rate of the falling material. Each microscopic droplet of molten alumina lands on the thin, liquid film at the tip of the growing seed, fusing with it before solidifying. Drop by drop, hour after hour, the material accumulates in a state of quiet equilibrium. Because this solidification happens continuously at a highly regulated temperature, the atoms have time to align themselves into a perfectly ordered, uninterrupted lattice. This deliberate rate of growth ensures that the resulting material is a single, continuous crystal, entirely free of the internal boundaries and grain structures found in common metals or poured glass. This absolute structural continuity is essential for the performance of the finished watch bearings. Without grain boundaries to create structural weak points, the synthetic crystal possesses a uniform, flawless consistency. When a microscopic watch pivot eventually rotates against the finished jewel, it will meet an identical, ultra-hard surface at every coordinate, with no structural seams to cause uneven wear or premature failure. Over several hours of uninterrupted operation, this gradual deposition transforms the shower of microscopic liquid particles into a solid, cylindrical ruby boule, glowing deep orange in the heart of the furnace. Once cooled, the solid corundum boule cannot be immediately sliced. The extreme thermal gradients of the flame fusion process lock massive internal stresses within the crystal lattice. To prevent spontaneous shattering, a technician splits the boule lengthwise along its natural parting plane, releasing this tension. This clean split transforms the single crystal into stable, raw stock, ready for the machining floor. Wafers are sliced from these halves using diamond-edge saws, then ground down to precise thicknesses. From these wafers, specialized machines core out tiny discs, drilling a central 70 micrometer bearing hole with a tolerance of just plus or minus 2 micrometers. Multiple polishing stages using progressively finer diamond compounds reduce the inner surface roughness to under 0.025 micrometers. Through this systematic reduction of scale, a single crystal boule yields the raw material for thousands of microscopic watch jewels. The finished watch jewels succeed because synthetic ruby is chemically identical to natural corundum. Ranking at 9 on the Mohs hardness scale, this material is second only to diamond. This physical hardness, paired with a sub-microscopic polish, provides a nearly frictionless surface for rotating steel pivots. A standard mechanical watch movement uses approximately 17 of these tiny bearings, while highly complex movements require far more. Positioned at every high-wear contact point, these lab-grown gemstones protect the wheels and pinions, ensuring decades of continuous, high-precision timekeeping. Today, even in our digital age, the mechanical watch endures, relying on a century-old flame to beat indefinitely. In a world of temporary technology, these microscopic crystals remain the silent guardians of permanent time. What heirloom do you wear? Tell us in the comments.